Good morning, everybody. As Brian had mentioned earlier, I'm Kyle Bradbury. I'm the director of the Energy Data Analytics Lab here at Duke, and I'm proud to be able to present our keynote speaker, Dr. Joseph DeCarolis. He is the administrator of the U.S. Energy Information Administration, and prior to his current appointment, he served as a professor at the Department of Civil Construction and Environmental Engineering at North Carolina State University, just down the road from here. His career and publications have centered on addressing energy and environmental challenges at the intersection of engineering, economics, and public policy. And his core research involves the development and application of energy system models to examine energy futures under uncertainty. So he's very much a thought leader in this field and has his fingers on the pulse of how the US gathers, shares, and transforms energy data into insights. And it's a true honor to have him here with us today. So please join me in welcoming Joe DeCarolis.
All right. Good morning, everyone. Thanks, Kyle, for the very kind introduction. And it's an honor to be here. I'm really happy to be back in Durham at Duke. So today I'm going to be talking about energy data analytics at the U.S. Energy Information Administration. The talk is broken down into four pieces. First, I'm going to give just a very brief overview of EIA and our mission. I want to talk a little bit about some of our recent data-driven insights. Then I want to talk about some of the priorities we have at EIA into the future, and I'll kind of apply a data analytics lens to that discussion. And then finally, I want to talk about where we see the frontier at EIA and some of the things that we want to work on. I'll also say it was really fun to put this presentation together, and I consulted with our senior leadership and senior analysts to put this together, so thanks to them as well. Okay, so again, just an overview to begin with. So the Energy Information Administration is a statistical and analytical agency within the Department of Energy. Being a statistical agency means, among other things, that we're vested with the authority to collect energy data from industry, and that's really important. It means that we are a critical source of energy information in the United States. I like to think that EIA data serves as the foundation on which our collective understanding of the U.S. energy system is built. The other point is that we operate independently. So when we produce data, when we produce reports, we're not asking permission to publish that. We operate completely independently of any other part of the Department of Energy or the rest of the federal government, again, when it comes to releasing products and what we say in those products. Just to give you a sense of scale, our fiscal year 2023 budget was $135 million. We have about 360 federal staff and another 300 contractors. As I mentioned, the data collection program is really foundational to our mission. On the supply side, gathering that data is our largest operational area, and it's used to produce more than 300 reports annually. We also, on the demand side, we have 3 large-scale multi-year consumption surveys. Many of you are probably familiar with these. There's the Commercial Buildings Energy Consumption Survey, the Residential Energy Consumption Survey, and finally, the Manufacturing Energy Consumption Survey. So very quickly, I just want to give you a sense of the scope for the data collection effort. So this is what our electricity data collection looks like. Anytime you see EIA dash and then a number, that's a survey that we have in the field. So if you do research on electricity, you probably are familiar with our 860, our 923, or 930, the hourly data. And you can see that, though, that we have surveys that cover all the way from natural resource extraction all the way through the flow of electricity to end-use sectors. We have a similar comprehensive survey collection or data collection program with respect to petroleum. Again, from the point of production all the way through the flows of refined products into the marketplace. Again, anytime you see a box on this slide, again, that's a different survey that's in the field. And then finally, this is natural gas, same thing. You see a box, survey in the field, It runs all the way from collection of production data all the way through the amount flowing into end-use sectors. We also produce a series of analytic products. Every month we produce something called the short-term energy outlook. That's actually an econometric model that we run every month. It looks at US and global supply, consumption, trade, stocks, prices, and energy-related carbon dioxide emissions. In the United States, the horizon is 12 to 24 months, and it's always through the end of the following year. So right now we're forecasting through the end of 2024. We also produce the annual energy outlook. That's probably our highest visibility analytic product. To do that, we use something called the National Energy Modeling System, which is a big complex model of the US energy system, and we look at US energy supply, consumption, and trade over a 30-year period. Right now, the model runs through 2050. We have our International Energy Outlook, which is sort of the global version of the annual energy outlook. We use a different modeling system for that. For that, we use the World Energy Projection System, again, looking at the same sorts of issues. We actually just released our IEO a couple weeks ago. And then there's a variety of other products. Every week we have a This Week in Petroleum, our Natural Gas Weekly Update. We also produce Today in Energy articles. These are really great. They're just short pieces. There's typically a figure and then a couple paragraphs. These are issues that our analysts are finding to be very interesting. And so if you're just looking to keep abreast of ongoing energy issues, this is a great, these ties are a great read, and I recommend taking a look at them. And then finally, we'll produce reports based on a congressional request or from key stakeholders. Okay. I want to talk a little bit about energy data analytics. Now, I don't know about you, but when I think about data analytics, it's kind of a vague concept. So I thought before I start talking about what we're doing, it would be good to define at least the way that I think about it. So in the process of pulling this together, I thought, well, I'll go to some authoritative sources and see how they define data analytics. So Amazon, AWS, this is their definition. Data analytics converts raw data into actionable insights. It includes a range of tools, technologies, and processes used to find trends and solve problems by using data. Google, you can see there, the first point is that they define data broadly. Sometimes we just think about data as, it's a number and a spreadsheet, right? And their point here is it's more than that, right? And I'm sure you're going to hear a lot about that during this workshop. Pictures, words, different types of observations, videos, those are all sources of data, and they define data analytics as the collection, transformation, and organization of these facts to draw conclusions, make predictions, and drive informed decision making. Our data analytics objectives at EIA are twofold. The first is that we need to process the data, derive insights, and then we want to provide those to the public. Right? But there's a secondary objective. We want to be able to collect, organize, and synthesize the data in a way that allows you all to derive insights by looking at the data yourself. I find it's useful to have a simple mental model for how to think about things. Obviously, energy data analytics, the data availability is exploding, the methods are exploding. So this is my simple cartoon for how to think about the way in which things are evolving. The top line with the dots is meant to represent, in many ways, the way that we've collected data historically at EIA, right? We do a discrete data collection at a defined point in time. It might be monthly, it might be annually. We collect, we process the data, and then we produce a chart, right? A bar chart. Where we're moving, right, is much more data availability. So we might still have those, we still do have those discrete data collections. The blue bars under the second series of dots, though, represent higher temporal resolution, right? So instead of just collecting monthly, in some cases now we're collecting hourly, right? So the frequency with which we're collecting the data is much, much higher. And the other thing, those yellow dots are just meant to represent there's all this other data that's out there, right? And we can ingest that data, not EIA data, but other commercial data, other government data. We can ingest that and, again, use that to derive insights. So the key is that instead of just producing simple graphics that tell the story, we need to be thinking in a much more sophisticated way about dashboards. How do we selectively reveal information to stakeholders in a way that allows them to derive their own insights. So in this section of the talk, what I want to do is go through some recent data-driven insights, and I'm going to try and build this up. I'm going to start with the simple things that are relatively straightforward, and then we're going to kind of increase the complexity or the sophistication and the analytics. So I'll start with small-scale solar. So we've added, in 2022, the United States added 6.4 gigawatts of small-scale solar, and we define small-scale solar as less than one megawatt installation, right? So a lot of this is rooftop, commercial buildings, residential buildings. That small-scale solar makes up about a third of the total US solar capacity that's currently being installed. And this is the thing that blew me away. The capacity additions from the small-scale solar are only surpassed by utility-scale solar and battery storage. Small-scale solar is growing faster than everything else. I think that's pretty interesting. And again, this represents a pretty straightforward data collection, right? We have a survey in the field. Every month we ask utilities, what are you planning to build? We track that data. We can produce a relatively simple graphic to illustrate that. This is partly cut off on the slide. Second topic is electric vehicles. Electric vehicles right now represent about 6.7% of sales. So that particular percentage is from the second quarter of 2023. This year, we've already, in the United States, have sold 1 million electric vehicles. And you can see from the chart that 6.7% share of new sales just looks like it's growing exponentially, okay? But to really understand what's going on, you also have to look at market segments. The luxury vehicle segment of the light-duty market is about 18%, okay? And in that second quarter of 2023, EVs accounted for 32% of total luxury sales and only 1% of non-luxury sales, okay? So a lot of the EVs that are being sold are in the luxury market. On the table here that got partially cut off here, this is looking at available models from 2021 to second quarter of 2023. So we're looking at differences. So when you look at non-hybrid internal combustion engines, your standard vehicles, there have been 21 makes and models that have been taken off the US market, and we've added 21 electric vehicle makes and models, okay? If you look at just the luxury segment, though, you can see that that's where the bulk of the change has taken place. Of the 21, 17 have been removed, of the non-hybrid internal combustion engines have been removed from the luxury market, and 19 battery electric vehicles have been added to the luxury segment. So again, once you start to look at market segmentation, you start to see where the electric vehicles are being deployed, and that informs our thinking about how this market might progress in the future. Totally different topic, looking at liquefied natural gas, or LNG. This is data actually that we're not collecting. This is being collected in the Department of Energy by Fossil Energy and Carbon Management. The figure on the left shows LNG exports from the United States by terminal. And here's the amazing thing. We started exporting LNG in the United States in 2016. We're now the largest global exporter of natural gas in the world. So some other interesting things here. You can see the COVID-induced demand collapse that happened in 2020, right? Demand cratered, nobody wanted to take delivery of that LNG, so we kept it domestically. The other thing that's interesting is that dark blue band represents the Freeport facility. Last summer, they had a fire, and the facility shut down. So you see those middle of last year, those dark blue bars go away. And that was a really interesting event because what we saw was price spikes both in Europe and Asia. And it's an indication that we really have this increasing global market for LNG. So something that happens at one LNG terminal in the United States is actually affecting prices around the world. On the right-hand side, this is looking at, of our LNG exports, where is it headed? You've got Asia on the left, Europe in the middle, rest of the world on the right. And I think the really interesting thing here is if you look at 2021, those middle bars to 2022, you can see that there's been a big shift from exporting LNG to Asia over to Europe, right? And this is a consequence of Russia's full-scale invasion of Ukraine and the US resupplying Europe where natural gas prices were quite high. And again, we monitor these markets extremely carefully. Okay, yet another topic. This is data that's drawn from our residential energy consumption survey. One thing I'll say just methodologically about this survey, so we're trying to survey homes to figure out what kind of equipment they use and what their energy demand looks like. We used to just put workers out in the field, literally with a clipboard that would go around and interview people. We used to collect about 5,000 responses, and we could generate statistics that were good at the census division level. Our folks have transitioned from that kind of field collection to doing web and paper-based mail surveys. We now collect 18,000 responses, and we can produce statistics that are significant at the state level. There's a lot that we could talk about just from Rex alone. I could give multiple seminars. I could give a whole seminar just on this one figure. This is looking at energy expenditures. This is dollars spent per square foot. And one thing I'll just call your attention to is the light green at the bottom here. This is by household income. And you probably know this intuitively, right? But lower income households, they tend to rent. The equipment tends to be older and less efficient. Well, we can put numbers to this now, right? So we know that household incomes that are less than $10,000 a year, those households are paying about $1.30 per square foot for energy. Households that are relatively wealthy that have incomes of $100,000 or more per year, they're paying significantly less. They're paying less than $1 per square foot, right? And again, we can go in and look by all of these different demographic categories and draw some really interesting insights. So this is a really large-scale consumption survey that we use that we apply analytics to derive insight. Okay, another example on the modeling front. This was a result that we presented in this year's annual energy outlook. One of the challenges with long-term energy modeling is trying to characterize future uncertainty. In NEMS, which is the model that we use, it's complex and it's really difficult to iterate. But what do we have a lot of, right? We have a lot of data. So we've been exploring different ways to characterize uncertainty with the data that we do have. One of the ways that we can do this is by developing what are called empirical prediction intervals. This is an existing methodology. If you've ever looked at like the hurricane cones, it's the same methodology that gets used to produce those. We're just applying them in a different way. And in fact, this was done by Kac et al. In 2017. They actually applied this method to the AEO, so they really teed it up nicely for us. Basically what we do is we have at EIA, we have a long history of producing these long-term projections, right? So what you do is you go back and you look at those past projections. For simplicity, we're just looking at our reference case, right? We look at our reference case, and then we compare it to what actually happened. The figure here is showing emissions, so we can say, hey, back in 1995, we projected in 2020 energy-related CO2 emissions would be at a certain level. What actually happened, right? So we can basically bin those differences by the length of the projection, right? So if it was a projection that was 20 years into the future, we can look at the delta between what we projected 20 years into the future and what actually happened. And then we can form distributions of those differences. And those distributions, again, can be organized by how far out the projections were made. There's a lot of different methodological details here. What we used in the AEO was this non-parametric method. So instead of assuming an underlying statistical distribution like a Gaussian, we just look at it empirically. And we can use this to derive this cone of uncertainty. And again, what you're seeing here is a cone of uncertainty for energy-related CO2 emissions. This was in this past AEO. So just to walk you through it, the black line represents the reference case. The two gray lines represent the most extreme emissions that we got across all of the cases that we ran in the AEO. And the blue cones represent this the uncertainty cones that I've been talking about. And I think this is really interesting, right? Because a lot of times people complain about our projections being wrong or being biased. So by forming these cones, what we're doing is we're looking at the actual difference between what we said would happen and what did happen, and that's informing the cone. One of the key things here is that we don't anticipate policy. We have a very strict interpretation of current laws and regulations. What happens? We get policy over the time horizon that tends to reduce emissions, right? But we're capturing that with this cone approach, okay? So again, uncertainty is really important. I think data analytics is a place where we can really expand our work. This is just one small example, and we're looking at this method as well as many others. All right, final example is federal financial interventions and subsidies in energy. As you might guess, in DC, there's a lot of interest in how is the federal government spending money on energy, where is it going, how is it being used, to which technologies and fuels. So we periodically get asked to do this. And it's a monumental challenge, and it's a lot of manual labor. So if you just think about award transactions, you get something like 80 million discrete federal budgetary transactions across 7 fiscal years. Like, that's a lot of data to sort through, right? Now, of course, we're just interested in the energy one. So we want to take just a narrow slice out of that really big pie. But the question is, how do you do that, right? So for the first time this year, what we did was we took that information, we uploaded it onto AWS, and then Amazon has this system called Comprehend, and it's a natural language processing service that uses machine learning to find insights and relationships. And so what we did was go through this classification process. So you basically train the service to classify information and then to just put it in different buckets, right? And so that's what we did. And then we applied it to all of the information that's out there on federal energy subsidies. And we were able to produce this enormous data set. And if you look at the timeline on the right, we were able to do this in a matter of months. I mean, this is something that we've never been able to do before. Every time we've been asked to do it, we do it for 1 year. You get a 1-year snapshot. This year, we were able to do 7 years all at once, and we were able to do it faster than we've done it in the past. So this is just a high-level result. I'm not going to go into too much details, but just so you know what you're looking at. The tax expenditures in blue, this is where your production tax credit, your investment tax credits for renewables, those would fall. We get that data from Treasury as well as the Joint Committee on Taxation, by and large. There's research and development funding. We take and break that into basic and applied. There's direct expenditures. So these are just congressionally appropriated funds that get transferred to recipients via federal agencies. And then finally, the loan guarantee program. And that's basically if the loan gets paid back, of course, it's not really a cost to the government. So this is incorporating the risk of default on those loans. So you can see the overall trend on the left-hand side in these expenditures, and there's just a couple very high-level insights. The tax expenditures have been the largest part of federal subsidies. We've had massive growth in wind and solar, which attract these subsidies, and so that's part of the reason those expenditures are so high. And most of these federal subsidies were spent on renewables, so it was primarily biofuels, wind, and solar. A lot of the subsidies were also spent on low-income households and to produce energy efficiency improvements in buildings. In fiscal year 2022, about 67% of the energy-related tax expenditures went to renewables. Okay? Again, first time we've been able to provide this kind of a record over multiple years. Okay, so I am going to talk about some of our priorities at EIA and discuss some ongoing work. So these are the high-level priorities. We want to modernize our IT enterprise. We want to make our information more transparent and accessible. We want to expand our energy modeling capabilities, and we want to be able to provide community-level insights into community-level impacts. Modernizing the IT enterprise. We're building a brand new data center. We're also shifting a lot of our data and analysis to the cloud. And the other thing that I think is really exciting is we're rethinking our data architecture from the ground up, right? So internally at EIA, we have a lot of siloed workflows where we have a survey, we collect the data, we process the data, and then we produce a spreadsheet and a PDF perhaps, right? What we want to do is build a data schema that can relate all of the data that we have across EIA. Okay? So one of the things we've been experimenting with is something called Dublin Core, which is a general taxonomy that allows you to organize information. So just imagine you have this big giant table in Excel, and you've got roughly 15 columns. Can you provide column headers in a way that allows you to uniquely identify each bit of data at EIA, right? And then once you can do that, it becomes extremely powerful, right? Because you can query the data in a unique way and create views, customized views of the data. So this is something that we're actively working on now. Once we modernize IT, rebuild this data architecture, that is going to enable us to make our data more transparent and accessible, which is has been one of my big priorities. We can build dashboards on top of the new data system to visualize, manipulate, and download that data. I think we do a nice job of providing dashboards. I have a couple snapshots here, like the hourly electric grid monitor. We also have a natural gas dashboard. But I think if you look at the totality of the data that we have at EIA, one of the things I've been saying internally is, right now we're kind of like the picture on the left. This is the dashboard of a Boeing 707. There's a lot of stuff, there's a lot of dials, a lot of knobs. We make it all available for free, but it can be kind of overwhelming and it's hard to know where to look, right? So the example that I'd like to move to on the right is you have a Tesla Model 3 dashboard, right? There's still a lot of information, but there's a lot of thought that goes into how you selectively reveal information to users in a way that doesn't overwhelm them. And again, think back to the definition of data analytics that allows people to realize insights. Moving on, we want to expand our energy modeling capabilities. First thing we're doing, you might have seen an announcement I made over the summer. We're taking a pause on the annual energy outlook. So unfortunately, in 2024, we won't be producing an AEO. But I thought that it was a really important decision because we really need to retool NEMS to incorporate different low carbon pathways like hydrogen, industrial carbon capture, seasonal storage, better representation of demand technologies. We're in a position with the passage of the IRA where once some of these provisions are finalized, we need to be able to model them because they are considered current laws and regulations. Independently, though, of updating NEMS, which we need to do, we've been hard at work thinking about a next generation energy modeling framework, okay? Why would we do that? Well, NEMS has been around a long time. We've been using it for about 30 years. Lots of things have changed, right? And so we want to think about a next gen framework. The quote you can see in the upper right there, that's actually taken from the bipartisan infrastructure law. This is language directed at EIA to migrate towards a single, consistent, and open source modeling platform. These are the characteristics of this new platform that we're in the very early stages of developing. It's going to be open source. We're going to make source code and data publicly available through GitHub. It needs to be nimble. We want to update it and change it quickly. It needs to be flexible. We want to handle diverse modeling needs. And we want to adjust model complexity to suit the question. It needs to solve quickly. If you do modeling, you know that that's always a challenge. It needs to be cloud capable. We want to make use of cloud resources. It needs to be modular. We want a separation between code and data. And like the existing NEMS, we want to have modularity in our representation of different sectors. It needs to be broad, right? It can't just be narrowly focused on energy. We need to be thinking about what about critical mineral supply chains, novel technologies. How do we model industrial policy like the IRA? How do we think about new market designs? It needs to be endogenous. So we don't want to make assumptions about how things will play out. We want to try and represent the dynamics of the market within the model itself. It needs to be granular. We need high spatial temporal resolution, especially if we're going to model high penetration of renewables. And it needs to be robust. We need to have this broad consideration of uncertainty. In my academic career, I've spent a lot of time trying to figure out how to embed uncertainty metrics into energy system models. I don't need to tell this audience that there's, there's a lot of uncertainty. The fact that we're in this period of rapid transition means that the uncertainty is actually heightened. And I just have a list here of all the things we need to be thinking about, right? Like climate change impacts, again, infrastructure and supply chains. How is international trade and security going to evolve over time? How is technology innovation going to unfold? What about novel technologies, particularly where we don't have a lot of data, robust data to characterize those technologies because they're at an early stage? Again, how do we model policy that's not a simple price on carbon or a carbon cap? Right? We got to make sure we have the knobs embedded in the model to be able to do that. We need to think about impacts on people. If we're deploying a lot of new infrastructure, we need to look beyond just emissions, capacity, energy prices, right? We need to think about where is infrastructure going, how does it impact actual people? Because of all this, we can't just look at uncertainty as a sidebar. It needs to be incorporated into the model, into the model framework itself. And then finally, we want to provide new community level impacts. We're trying to find ways to leverage our consumption data. So the three big consumption surveys in ways that can produce new insights at the community level. Given time, I'm not going to go into a great amount of detail here, but one example that was brought to my attention is, you can start by doing things like taking the REX data, the residential sector, and then overlaying it with data that comes from the Alternative Fuels Data Center out of EERE, Energy Efficiency and Renewable Energy at DOE, and start to look at, you could start to generate some pretty interesting insights just by doing that. All right, so where's the data science frontier at EIA? Where are we headed with our work? I've broken this into two categories. First is how we might use data analytics and AI internally at EIA. The first is natural language AI to process, analyze, and summarize information from our public email boxes. We actually have a data science pilot program within EIA right now to take our analysts and train them up on the latest in data science techniques. So this is their little practicum, is to basically look at all our public inboxes over the last period of time, apply AI to provide summaries and insights into the feedback that we're receiving from stakeholders. A second thing is to construct a sampling frame for a population of interest. This is something I've actually been talking with Kyle about. You take something like the Commercial Buildings Energy Consumption Survey, or CBEX. It is a massive, massive cost to us at EIA because we ourselves have to build a statistically representative frame of all the commercial buildings in the United States, right? It eats up enormous resources, and it's literally done by contractors who, again, go out in the field and do research and identify commercial buildings to come up with this survey frame. Can we use, again, additional data analytic techniques like satellite imagery can we ingest that data and use it to help build the frame? I think that's definitely something we're interested in. Just applying machine learning methods to detect unusual data or anomalies. I mean, given the scope of our data collection program, you can imagine that we encounter this all the time. And so can we use some of these techniques to get better at that and more efficient? And then finally, improve the development of our code through generative AI support. I personally I have like some pet projects where I code, and I started using ChatGPT to just give me some basic information, help me write a Python function that returns whatever. And it is amazing. It is truly amazing. I just thought it's a whole other topic, but I mean, I think that's another area where we have analysts, most of them are not computer scientists, they're statisticians, mathematicians, they're engineers. Using generative AI support to help develop code, I think, is another area that we're interested in. The second piece here is how we would use some of these techniques to provide more information to the public. These are just some examples. Many of these things are actively being discussed and worked on. So one is identify which factors have the largest impact on well productivity, both petroleum and natural gas well productivity. We produce a drilling productivity report, and we're starting to analyze the reams of historical data that we have to say, what has actually driven changes in productivity over time? A second example is a new electricity grid operations dashboard that could pull together different data streams. So one example is we get hourly data from the RTOs, but it's by fuel source. And EPA has SEMS data at the unit level, but it's historical. Can we use data analytics to pull those together and provide unit level hourly generation? You know, that's the sort of thing that I think is possible. I've been thinking a lot about long-term model benchmarking, right? Kind of along the lines of what I discussed with the uncertainty cones. I really want to be able to track what did we project was going to happen, what happened, what can we learn by comparing observed outcomes with model outputs, and as part of that, can we develop energy transition indicators that help point the modelers in the right direction? So if something really starts to change in an unexpected way, we can identify it early and then incorporate that into the modeling. There's a lot of opportunity, I think, to provide real-time situational data to stakeholders during high-impact events. We already do that to some degree, but I think there's a lot of ways in which we can advance the data analytics to do it more effectively. Apply statistical methodologies to multiple energy and demographic data sets, again, to provide community-level insights. And then finally, we have so much information on our website. There's data sets, there's a lot of written materials, from Today in Energy article all the way up through our annual Energy Outlook. Could we apply natural language AI on top of all of that, train it on our data and our analysis so that as a stakeholder, you could someday go to the EIA website and just ask it a question, right? And it will give you what you want. It'll produce a figure or a table or give you some text, right? That is very forward-looking. That's not something we're actively looking at, but I think like many organizations, right, this explosion of AI over the last year or so has really got us thinking about what we might be able to do. And then final thing, I have one more slide, and it's just a word of caution, okay? Anscombe's quartet. So I'm going to get back into professor mode for just 1 second. So do any of the students, have you ever heard of this? Anscombe's quartet? Yeah? Faculty, not allowed. Okay, so you should investigate this. So Anscombe's quartet was constructed in 1973 by a statistician named Francis Anscombe. He developed 4 data sets, and they have, so you can see the table here, and the thing is, they have nearly identical descriptive statistics, okay? Mean, variance, basically all the same. If you graph it, if you graph each of the data sets, that's what they look like. And his point was, you need to be able to visualize the data, right? You can't just rely on statistics. And so this is just a note of caution. You know, one of the things that I worry about with data analytics is as we do this, and of course there's enormous opportunities here, we need to be careful because we're removing ourselves even further from the underlying data, and we need to just keep this in mind as we progress these methods. And with that, I will happy to take any questions.